Hello, this is a video on Intro to Counting, the Introduction to Counting, which is a way of determining how many ways something can be done. Some method of counting that you may have seen would be to count how many combinations there are in a lock. So your typical combination lock that you have here at school has 40 numbers, and you ask yourself, all right, what could the first number be? Well, there are 40 possibilities. What could the second number be? 40 possibilities. What could the third number be? 40 possibilities, for a total of 64,000 possible combinations. Now, this calculation is actually giving us a total that we don't know if this is entirely possible. There may be situations where maybe we're not permitted to have repeated numbers, or I certainly would doubt that they have combination locks that you repeat the same number 3 times. Then we'd be able to subtract those out if we needed to. But what you've done here is you've used the fundamental counting principle, and that is how many ways are there to do something times how many ways are there to do something times how many ways are there to do something, etc. And these ways to do something, in the case that we just looked at, I mean, it was how many ways are there to get the first number, how many ways are there to get the second number, how many ways are there to get the third number. Another example would be, say I'm looking at I've got 5 ties, 4 shirts, and I've got 3 pairs of pants. How many possible outfits do I have? Well, the fundamental counting principle says 5 choices for the first, 4 choices for the second, 3 choices for the third, multiply them, and there are 60 possible outfits that I could get, not taking into account that there may be some matches that I don't like. That is the absolute number of possibilities. Again, that is the fundamental counting principle. Both of these are actually permutations. Permutation is when I have some choices to make, and I can mix and match those choices however I want, and essentially apply the multiplication principle to determine all of the possibilities. So that really is a permutation. Now, the thing that we want to do is we want to compare permutation with combination. So there's the combination and there's the permutation. Now, this combination you might recognize from the binomial theorem. So the formula for the combination is n things taken r at a time, and that's how you would read this. You would say, how many ways are there, or what are the possible combinations of n things taken r at a time? Now, what does that mean? That would mean that if I have 3 things here, say I've got thing A, thing B, and thing C, how many ways are there to take them if I take them, say, 2 at a time? So 3, choose 2, and again, if you watched a previous video or maybe some instruction that you had on the binomial theorem, you know that you can read this as 3 choose 2, or you could read it as the combination of 3 taken 2 at a time, and that's saying how many ways are there to take 2 of these. So I could take well, let's not list them up here. Let's put them down here. I could take AB. I could have BA. Nope, I can't have BA. I'll talk about that in a second. I could have AC, or I could have BC. And the thing about combination is that order doesn't matter. Does not matter. Order doesn't matter. So what happened here, AB, BA, I just tried to say that BA is different than AB, but it's the same thing. They're both an A, they're both a B. The order doesn't matter. So I'm going to drop that off. And I'll talk briefly about, so what did that have to do with our binomial expansion? So when I went and I looked at x plus y to the 4th, say, so I went x to the 4th, and then I went plus 4x to the 3rd, y, plus, and then it was the combination of 4 taken 0, 1, 2, taken 2 at a time, times x squared. So this is just I'm doing a little application of the binomial theorem. Well, why does this give me that exponent? And the reason is that if I have x plus y and I write that 4 times, 1, 2, 3, 4 times, and then when I do this expansion, when I expand all this, I'm going to have a term that has an x squared in it, right? And the question is, how many of these x squared terms am I going to have? And the answer is, how many ways are there to get 2 of these x's? Like I could get that one and that one. That would be one way. I could get the first one and that one. That would be a way. I could get the first one, and that would be a way. So I'm counting up all of these ways, and all of these ways can be counted using this combination notation and the formula to determine that, yes, there are actually 6 ways of doing this. 4 choose 2 is equal to 6. And you could actually count those up by looking at all of the possible ways that you could combine the x's down in this with these factors here. Okay, so that was just relating that to something that you've maybe had a question about. Now let's go on to permutation. So the notation for permutation is here, and it's the permutation of n things taken r at a time. And the permutation of 3 things taken 2 at a time would be a, b. Now here, order matters. So if you look up here, it says order does matter. So in that case, I'm going to be able to say that BA is a different pair. And then I can go AC and say that CA is a different pair, BC, CB. So these pairs are different. And then what we would want to think about is why, what does it mean, like what would be a situation where order matters or order doesn't matter? So we could think about, well, I'm going to take, these are A, B, and C are 3 people, and I'm going to choose 2 of them, and they're both going to get $5. All right, so it's the same thing. It doesn't matter if I go A, B, or BA, they're both getting $5. Now compare that to if I took, and I said, all right, I'm going to choose from these 3 people, and one of them is going to get $5, and the other one's going to get $10. Well, now it's going to be different. I mean, this could mean that A gets 5 and B gets 10, and then this could mean that B gets 5 and A gets 10. So that would be a situation where order matters. Okay, and finally, we have, if we look back at our original page here, we've checked these off, right? We've checked off the fundamental counting principle, checked off permutation, checked off combination. So we're just going to look at permutation with the repetition, which is a pretty specified type of counting, and it's difficult to find some interesting applications for this, but it is in most textbooks, so I'm going to go ahead and address it here. And the idea here is if I take 3, or if I take, not necessarily 3, if I take some letters, say A, B, C, D, A, and I say how many ways are there to rearrange these letters? So it's not like the previous page where I had a pool of letters that I was drawing from and I was only going to take some of them. In this case, I'm going to take all of them. So obviously, if I'm taking all of them and saying that there are different ways to rearrange them, then of course it is going to be a permutation, because order obviously is going to matter. If I'm going to say that I have different variations on arranging these letters and say that it's different, then order is going to have to matter here, which makes it a permutation. And then this is actually, it's a permutation, and it is a permutation with repetition, and the repetition being because I have an A and I have an A. Well, there's a neat little shortcut here. Again, we could look at listing these out. So if I go B, A, C, D, and I'm probably not going to get very far before I decide, well, this is way too many to list out, list all these out. and recognize that it is a permutation with a repetition, and the way that we calculate that is to take what's the total number. Now, if they were all different, this would be it. It would be 5 factorial would be the number of ways that I can rearrange these. And think about why that would be. It actually goes back to the fundamental counting principle, which would say, oh, there's 5 spots, and there's 5 ways to fill the first spot, and then once one of the letters is gone, I have 4, and then 3, 2, 1. So that would be 20, 60, 120. So there's 120 ways to rearrange the letters if the letters were all different. But here, they're not all different. 2 of the letters are the same. So if I might take this one here. We'll just take this one down here since it's convenient. If I take this down here and I say, hey, here's a different one, and you say, well, that doesn't look any different, and I say, well, actually, I switched the A's, because one of these A's, well, I could just call it A1 and A2, and then I went A2 and A1. Well, yeah, so I kind of switched them, but we're not going to count that. We're going to say, look, they're both A's. There's no way of distinguishing between them. So what I'm trying to add on here as a different variation, I'm not going to count that as a different variation. So the way that we count that is we take the 5 factorial, and then we take any repetitions and say, how many times do they repeat? So I take the A, and it repeated twice, factorial. And that's going to give us the total number of ways. Now, do you know how to do 5 factorial divided by 2 factorial? Do you know you're just going to end up with 5 times 4 times 3. And then the 2, 1 in the numerator cancels with the 2, 1 in the denominator. So that's 20 times 3. So there's a total number of 60 ways. Okay, so that's a brief intro to counting. These problems get really interesting and really challenging really quickly. So the idea is to understand these basic concepts, and then you just need to get your feet wet and figure out the ways that you can combine them and the situations in which you can apply them in order to count up the number of ways that something can be done. So you will have an opportunity to do that in the days ahead.